Hello kids, in this video we're going to talk about related rates. And these are how things change over with relation to time. And I've got four fairly classic examples for you when it comes to related rates. Related rates is a topic that can stretch its legs out as far as optimization can, but ultimately I feel like it's easier. A hot air balloon rising straight up from a field, level field, like that exists, is tracking by a rangefinder 500 feet from the point of liftoff. So this little side here is 500 feet. At the moment, the rangefinder's elevation is 45 degrees. So just create ourselves a little right triangle. 45 degrees. And we would have some kind of side X here. The angle is increasing at a rate of 0.14 radians per minute. How fast is the balloon rising at the moment? So we've got an angle. We got a right triangle. It says elevation angle, which relates to angle of elevation. This should give us some SOHCAHTOA vibes here. Okay. Now, it's worth noting we could solve for X here. But solving for X would be a waste of time because it's asking how fast is the balloon rising, not what the height is. If it was asking for what the height is, this would be just a regular angle of elevation problem. But this is a calculus class we're in. So we have to think to ourselves, we've got the angle of reference, we've got opposite, and we got adjacent. So that would be tangent we're working with. So I've got the tangent of theta. Okay, we're not going to plug in 45 yet. We're going to wait. We're just going to set up the formula. Okay, opposite would be the X, and the adjacent would be the 500. Now let's really quickly address something. Why am I not plugging in theta, but I am plugging in 500? Simply because the 500 is a constant distance. They're keeping the rangefinder at a set point, 500 feet from the point of liftoff. Since it is constant, we can just go ahead and plug it in. While this balloon rises, the angle of elevation of the rangefinder is changing. So we don't want to plug that in until after we differentiate. So this is going to bring back some memories of implicit differentiation. So we're going to think, what's the derivative of tangent? That would be secant squared. Secant squared theta. But when you're talking about rates, you're talking about, again, a change over time. So we're not differentiating with respect to x or y like we normally would. We're differentiating with respect to time. So we're going to multiply this by d theta dt. Okay? And then remember, this x over 500 would just be 1 over 500x. That would just give me a derivative of 1 over 500. But once again, we're not differentiating with respect to x or theta, so we have to write dx dt, the t standing for theta. Okay. Once we differentiate, we're good to plug in everything. Now, we got a couple things we have to contend with. First of all, the angle is in degrees and the rate is in radians. So we have to convert one or the other. So I'm going to actually convert 45 degrees to radians, and I'll let you review that. But it should be pi over 4. You can do the calculation or you can look that up on your unit circle. So pi over 4 is going into theta. So secant squared pi over 4. And then times d theta dt. This rate of 0.14 radians per minute, that would be d theta dt. It's the rate of theta per time in minutes. So we're just multiplying by 0.14. And notice how fast is the balloon rising? Well, the height was what x was. So that means dx dt is how fast is the height changing over time. So we're looking for dx dt. So what I'm going to do actually is I'm going to multiply both sides by 500. Okay. Get that out of the way. So we just have one calculation. that we can plug in to solve for dx dt. And then you would plug this into your calculator. Okay, so you plug that into your calculator and you get 140. Now, what's our label? What are we talking about here? Well, we were per minute, so that's going to be something per minute. Well, our height was measured in feet, so it would be feet per minute is dx dt. So a police car is approaching a right-angled intersection from the north, is chasing a speeding car that has turned the corner, is now moving straight east. When the cruiser is 0.6 miles north of the intersection and the car is 0.8 miles to the east, the police determine with the radar that the distance between the car is increasing at a rate of 20 miles per hour. The car is moving at a 60 miles per hour at the instant of measurement. What is the speed of the car? Okay, so there's actually a clarification I need to make because I did not type this out very well. This is actually the police car speed, right? Okay, so that's a little detail I left out. So that's the police car. Okay, now this problem would best be illustrated if we drew it out kind of like on a coordinate plane. Okay, draw my little arrows so my Calc 3 professor doesn't take off. Okay, so we have a police car heading south. Okay, the instantaneous it gives us is at 0.6 miles. Okay, and the car is heading east, and it is 0.8 miles. All right. Now, the police car is moving at 60 miles an hour. Let's call this Y, okay, since it's on the Y-axis, and we'll call this X, since it's on the X-axis. This might make you think that dy dt, since it's a rate, is 60. But since it's moving towards an origin point, it will actually be negative 60. Remember that velocity has positive and negative values based on is it moving away or towards something. If it's moving away, the velocity would be positive. If it's moving towards, then the value would be negative. So this would be negative 60 miles per hour. Okay. Now, the car speed is increasing at 20 miles per hour. That's not dx dt. That would be this side, which we could call dz dt. And since this line itself is not moving towards an origin point, as one car is moving away and the other is moving towards, this rate would be positive. So 20 miles per hour. Now, we're looking at a right triangle, okay, with two sides given. We're going to use the Pythagorean theorem on this side. Now, we do need z because nothing is constant in this instance. In the last problem, we had a side of the triangle where the radar was set up a fixed distance away, but both cars are moving, which means all three sides of the triangle are constantly changing. So we do need a side here. So really quickly, I'll do that up here. We got x squared plus y squared equals z squared. We have 0.6 squared plus 0.8 squared. That a little more defined equals z squared, and we get 1 here is equal to z squared. So that means z is equal to 1. And I'll do a bulk of my work down here because we're also going to use that Pythagorean theorem as our setup for the derivative. Because again, before we take the derivative, are any of these values remaining constant? And the answer is no. So the derivative of x squared would be 2x. But again, we're related rates. We're taking with respect to time. So we're going to multiply by dx dt. Same idea with y. The derivative is 2y, but with respect to time, so it's dy dt. And then z, same idea, 2z dz dt. Now, We could do a little bit of simplifying that there's 2's that cancel out here, and then we're just left with the remaining formula. So this, once you calculate your derivative, this one we can plug in values. X would be 0.8. Okay, dx dt, we're looking for what is the speed of the car. So times dx dt plus y, that was 0.6. And then dy dt was negative 60. Z, that was up here, that was 1, times dz dt, that was 20. We actually don't have to do any conversions. I didn't make mention of this, but the distances were in miles and the rates were in miles per hour. So that's good. So we got 0.8 dx dt, so 0.8 dx, and I'm actually going to run out of room, so I'll probably talk through most of the work. 0.6 times negative 60 would be minus 36. So I'm actually going to just go ahead and put minus 36 here. Okay. Minus 36. And of course, 1 times 20 is just 20. We'll add 36 to both sides. We will get 56 and then divide by 0.8. When you do all that, dx dt ends up giving you 70 miles per hour. There you go. Calculus in a high-speed car chase. All right, and another classic related rates problem deals with water running into a conical tank. So that's a cone. Let's see how well I can draw a cone. All right. That looks good. I like that. And it is rising at a rate of 9 cubic feet per minute. So notice that's related to volume because the feet are cubed. The tank stands point down and has a height of 10 feet and a base radius of 5 feet. So we got the base radius is 5 feet. And then from the top there to the bottom tip, it's 10 feet. Okay. How fast is the water level rising when the water is 6 feet deep? So we're talking volume here. Okay. Volume. That should be our context clue. So we need to know the volume of a cone. You can look this up. Pi, 1/3 pi r squared times height. Okay. Now, we've got two variables here, which means if we don't simplify this down somehow, we're going to have to use product rule. But let's not do that. Let's go ahead and figure out a way to simplify it down. So notice that at the beginning, our height is 10 feet and our radius is 5 feet. So that means our height is equal to 2r. That will be constant no matter what. So when you're talking a height of 6 feet right there, apparently it's green water. Don't drink it. The radius at said point would be 3 feet. Okay. But notice it wants to know how fast is the water level rising. That implies height. And how fast, again, we're talking about related rates here. So we're looking for dH dt. One thing I haven't pointed out yet that I will point out now is it's always important to understand what are you looking for before you start plugging in stuff, because then you can either make your life very easy or very complicated moving forward. So by identifying how fast, again, related rate with respect to time, is the water level rising, we're talking about dH dt. So if we plug this in right now, we're making everything in terms of r, which we don't want. So I'm going to go ahead and actually divide by 2 and say r equals h over 2 and plug that into r here. So let's rewrite this formula. 1/3 pi. Instead of radius, it's h over 2. But it's still squared. And then times the original height. Now we've got everything in terms of h. We should simplify a little bit. consider this to be 1/4 squared. That'd be, or 1/2 squared would give me 1/4. 1/4 times 1/3 is 1/12 pi. And then we have h squared times another h is h cubed. And that'll be a lot nicer to deal with. So when we do our differentiation, we get dv dt. Bring the exponent out in front. Ouch, that hurt. And then subtract 1. So 3 times 1/12. Talking it out, that'd be 3/12. That simplifies to 1/4. Okay. You can even look at it as the cubed from h would cancel out this original 1/3, and the only thing left would be that 1/2 squared. Pi is a constant like any other. And then we get h squared, and of course we're differentiating with respect to time, so don't forget your dh dt. Okay, and then this is part where we can plug everything in. We know height is to be 6 feet, so we got dv. Well, actually, I won't even do that because we have dv dt as well. Oop, too big of an eraser. dt. This right here at the beginning, that was dv dt because it was changing a volume with respect to time. So we can put that in right there. 9 1/4 pi, and then height, when was the height? It was at 6 feet. So times 6 squared times dh dt. So let's talk this through a little bit. You have 6 squared is 36 times 1/4. So 36 times 1/4 would be 9. So we end up with 9 equals 9 pi dh dt. And then you just divide by 9 pi. And that would be, the 9s cancel out. You're left with 1/pi feet per minute. Remember, height is still a linear measurement, so it's feet, not feet cubed, is dh dt. So the final example is the all-time classic example. If you were to ever watch TV shows where they try to script in calculus problems because the characters are in high school or whatever, they're probably going to talk about balloon problems. They're very common in calculus. So we have a spherical balloon is inflated with helium at a rate of 100 pi cubic feet per minute. How fast is the balloon's radius increasing at the instant radius of 5 feet? So we got, again, volume. So we need to know the volume. I'm not going to draw it out this time since I got lack of space. Volume of a sphere, again, if you don't remember this, look it up. 4/3 pi r cubed. Okay. So nothing to look for in terms of simplifying down variables. We just can go right to differentiating. So we got dv dt is equal to 4/3 pi. Actually, sorry, I'll illustrate so that should be 4 pi. Okay, so 4 pi r squared. All right, and then our dr dt. Now our dv dt, that was that 100 pi we're given at the beginning. We got 4 pi, and they ask us at an instant radius of 5 feet. So that'd be times our 5 squared times dr dt. 5 squared would be 25, times 4 would be 100. So we have 100 pi equals 100 pi times dr dt. Well, we can tell at this point dr dt would be 1. If you don't believe me, divide 100 pi by 100 pi, and you get 1 foot per minute is our dr dt. Now this one will take the extra mile. How fast is the surface area increasing at that instant? So surface area for a balloon, for a sphere, would be 4 pi r squared. Let's take a moment to appreciate that the differential of the volume is the same as its surface area. I always found that to be an interesting factoid. So how fast is the surface area increasing? Let's differentiate. dA dt is equal to, use our power rule, 8 pi r dr dt. Now we're referencing back to our 1 foot per minute and our radius of 5 feet. So dA dt, 8 times 5 would be 40, times 1 would still be 40. So 40 pi, we're in area now, feet squared per minute. So this is effectively saying at the moment our volume is increasing 100 pi cubic feet per minute. Our area is changing at a rate of 40 pi feet squared per minute. I won't write that out, but that's how you would describe that. Thanks for watching.